Hi everyone. Okay, in this video we are going to study Bayesian linear regression. The idea is to continue learning Bayesian inference by studying a different model. This model is a bit more complicated than the one we studied in the previous video, but at the same time it's going to bring new learnings and it's something way more applicable to real cases. What we're going to do here is basically grab again our linear regression model that we studied a few tutorials away and endow that model with uncertainty quantification capabilities. So just a quick recap on the model setup. I'm going to repeat again what we studied before in our tutorials of traditional linear regression. Basically, we have our training data set of input-output pairs x, y, where x can live in any dimension and y is our continuous one-dimensional variable that we want to predict. So in the linear regression setup, we are going to assume that each of our y predictions is going to be a function of the input xi plus an error. And that relationship will hold for every single point. And we will assume that the errors are normally distributed with mean zero and variance sigma square, meaning that for every data point, the error is going to have the same distribution. This is going to be the variance parameter, and we are not going to learn it. We are going to assume that that parameter is given. Okay, and finally, one of the most important assumptions in the linear regression model is that the function of the input is a linear combination of the input variables, right? So we can also write this in a probabilistic fashion where instead of predicting yi, we can tell that the probability of yi equals to certain value, given the input xi and all the parameters, is going to distribute normal centered in the linear combination of the input xi with a variance sigma square. And this is a direct conclusion of the fact that we are assuming that the errors are normally distributed with mean zero and variance sigma square. Remember also that we can use matrix notation. It's way more convenient considering that in general we have a bunch of data points, so we can put them all together in matrices. Our y's are continuous numbers, so they will be a column of size n times 1. Our matrix x is going to contain all the input. Remember that we are adding a column of ones because there is one bias parameter beta 0 in our vector of parameters w, and don't forget that these are the parameters that we want to find. In our case, we're not going to find the parameters directly, we're going to find a posterior distribution of our parameters w. So we can use the matrix notation like here and use capital Y is going to be the matrix product, in where this is exactly the function applied to our matrix x instead of the data point xi. Okay, remember also that in the previous tutorials we learned that we can use the kernel tricks to have nonlinear predictions, but still using a linear model. And how we did that? We used kernel functions. In this case, for example, the polynomial kernel function that takes the input and applies some modification to create more columns or more dimensions. And at the end, we end up in a nonlinear prediction. In this case, is a polynomial prediction, right? And also, remember, we saw the exponential kernel in where we can have a way more complex prediction now by applying this kernel function that is an exponential function of the distance between every data point xi and a set of basis functions noted by mu. So here's the link to the YouTube video. Make sure you saw that video and you understand very well that part, because I'm assuming here that you already know that. Okay, another assumption we are going to make here, and I'll explain that very soon in this video, is that the precision term, meaning 1 divided by the variance, is positive. Okay, so what means to be Bayesian when it comes to linear regression? As you know already, we are not going to try to estimate the optimal W as we did in the traditional regression setup. We are going to estimate a posterior distribution of W given the data. And how we do that? With the Bayes theorem, in where our posterior is the product of the likelihood times the prior divided by the marginal likelihood or the evidence. So let's go. Let's start finding the likelihood. As you know, the likelihood is the probability of the data given the model, meaning this, our data points are the input pairs x and y. So this is going to be our D. And in general, the x are our model inputs. So we can always put them in the right side and assume that those x are given. And the idea is to estimate the probability of the y's. And remember that instead of dealing directly with the X, we are going to create our phi matrix, meaning the matrix with the kernel tree, right? So let's use this notation for our set of data inputs better. And also remember that the parameter sigma square is given. And here we are multiplying sigma square by the identity matrix to create this effect. We know that the error are all independents, so there's no reason to assume that there are any dependencies among the different variables involved in our d-dimensional problem. So that's why we use a diagonal matrix. And in this case, the identity matrix is helping us a lot to create this diagonal matrix by just multiplying sigma square by the identity matrix. Okay, another thing we can do is instead of writing every single y here in the left side of our factor, we can just write this way with the product from I equals 1 till n, because we are assuming, as in most machine learning setups, that our data points are independent and identically distributed. If that didn't happen, it means that there is some sort of relationship between the different points, meaning that if we shuffle the data, we would affect the underlying patterns we are finding. So in that case, we need to do some sort of preprocessing to get rid of that. But for this setup, we're assuming that our data points are independent and ruled by the same distribution. And that distribution is the normal distribution, because we saw at the beginning that because the errors are assumed normal, then we have a normal distribution centered on the linear combination of the input data points phi of x. Remember that this is the equation for the normal distribution. In this case, it's multivariate normal distribution. I'm gonna super quickly recap this, but basically here, this term is an exponential function of the dot product between these two vectors, and each vector is the difference between our data point and the mean of the distribution. And the covariance matrix is somehow governing the way we make this dot product. So let me explain quickly this. This is the spherical two-dimensional Gaussian distribution. The spherical cases when we have that our covariance matrix is the identity matrix. Having a circle here means that there are no specific correlations between the variables involved in the distribution. If we start, for example, adding some stuff like increasing the variance of the second variable, okay, and keeping the first one the same, still there is no correlation between both variables because we have that the out of diagonal terms are 0. We are assuming a bigger variance for the second variable, and that's why we start getting this shape, right? A longer shape across the second variable. And if we start adding correlations, we can see that now the shape of the ellipsis changes. And now that we are assuming certain correlation between both variables, the shape of the ellipse changes and adopts this shape, showing that there is a correlation across this diagonal that passes between both variables. So, and why this is important? Because at the end, the shape of the matrix is going to change the way we make this dot product. This is also known as the Mahalanobis distance. As you can see here, it's exactly the same term that is inside the exponential, but what this is basically doing is like if we were to calculate the distance between these two green points and there is a correlation between these both variables v1 and v2, what the covariance matrix does somehow is normalizing and making sure that we are taking that correlation into account. So that effect is the same we get in our normal distribution, and that's why the normal distribution has this covariance matrix in the middle of the dot product. Okay, so if we replace our parameters in the generic formula of the normal distribution, we get this result. Since our covariance matrix is just a diagonal matrix, we can take that out of the dot product because it's going to multiply every term resulting from this dot product between these two vectors. So here our main variable is y, right? And the mean is the linear combination of our design matrix governed by the parameters w. And this is a constant term. Okay. So we can replace our probability by the equation of the normal distribution with these parameters. And what we can also do is to use matrix notation instead of the product now to make it more compact. So we can have this equation. Given that this term is constant, we're gonna get rid of it later, and you will see that we will deal with this distribution just by using the exponential term. Okay, for the prior, we will assume that the prior distribution of our W is gonna be a normal distribution with mean 0 and variance alpha square. That's a common decision usually for this. And again, we are multiplying alpha squared by the identity matrix to create this effect. Remember that W is a vector that lives in the d-dimensional space. So we need to have a variance for each of the variables. And we don't have in general any strong reasons to believe that there are any correlations between the parameters in the W vector before seeing any data. So that's why we assume that this is a diagonal matrix. Okay, again, one of the assumptions is that the precision term is positive and that this is a given parameter. So this prior is telling basically that before seeing any data, we will believe that our beta parameters are very close to zero, and how strong is our belief about the closeness to zero is going to be governed by the variance of this distribution. So the bigger the alpha, we are going to give more space to have initial betas that are farther from zero. So by regulating alpha, we will regulate the strength of our prior. Again, I'm writing here the equation of the normal distribution so we can replace the parameters of this normal into the equation, and you can see that we end up with this thing. So this is the covariance matrix, is again diagonal, so we can pull it out from this product, and since we have W minus 0, we're just going to have W transpose here. So this is the equation, okay? Again, we have this term that is constant, so we can get rid of it and work with a proportional term for the posterior. So we have the likelihood times the prior. So far, this is what we have. We found the likelihood and the prior up to 2 constants. And now we see that these 3 terms are actually constants. So we can get rid of them. And now we can say that our posterior is proportional to the product of these 2 exponentials, right? Why we don't care so much about constants here is because we know at the end that we are going to obtain a normal distribution as the result of this. So by understanding the parameters of that normal distribution, we will know exactly what is the constant term of the final distribution and what are the mean and the covariance matrix. So we're not going to need to calculate those. And in order to get to that point, we only need these exponential functions in the process. So now we can start developing this product further. We have the product of 2 exponentials. So now we can go and add both terms like here and multiply these 2 vectors and develop this multiplication here. Let's rewrite this equation, and now we can push in the sigmas, as you can see. And after that, we can factor by W transposed from the left and W from the right. So we end up with this equation. Now we are going to use a very cool trick. This matrix factorization trick is going to allow us to go to a normal distribution out of this exponential term that we have up here. Why? Because we know that if we have our product written this way, then for this equation, which is a generic normal distribution with these parameters, we can see that in the exponential part, we have exactly this product of matrices. If we can rewrite our current state of the posterior in this form, then we can conclude that our posterior is exactly a normal distribution with these parameters. So summarizing, we have the current equation for our posterior. We want to see how we can rewrite this equation in this form such that later we can conclude that our posterior is a normal distribution with these parameters. So at the end, we need to find lambda and mu such that this mapping is possible. Fortunately, this is not so hard. Why? Because that equation is kind of like close to what we want. If you can see here the colors, the green line is a straight mapping, right? We can see that we have exactly this form here, so we can conclude lambda almost immediately. Then the purple line is telling that we need to make these 2 terms equal to find mu, and what we have in the blue line is going to be the constant term because it doesn't depend on W. So let's start with the green term. As I said, it's straightforward. As you can see, it's W transpose times something times W, so this something in the middle is exactly lambda. Okay, so we already found lambda, and now we need to find mu. And for that, we assume that these 2 terms are equal. By the way, why these are equal? Because these 2 terms are the only ones containing W transpose. We don't have W transpose here or here, right? So we know that this is the only way to match these 2 equations is by matching these 2 terms as well. Okay, this term must be equal to this term. We can work a little bit here. We can eliminate the minus 2. Also, we can eliminate the W transpose, and we end up in this result. So mu is going to be this product We already know lambda, so we can replace lambda here later. Okay, we have the value of mu and lambda, so now we have our normal distribution. Why? Because we know that our posterior can be written in this specific way if we use lambda and mu as we express here.